Okay, for this question, we are given the table of values for a function and its derivatives with a few missing, and we're asked to evaluate some of the following things below. So, it has given us a, b, c, and d are unspecified constants, so we don't really know what they are, but we do have information about the first derivative, the second derivative, and the integrated function everywhere. So, let's have a look at this first question. Evaluate the derivative of f of x squared when x equals 2. Okay, so this is simply a chain rule question. If we apply the chain rule to this question, we know that that is going to be equal to 2 times the derivative of f of x, which is the derivative of this, times by f of x, by the chain rule, at x equals 2. For x equals 2, we have got the derivative function equals to minus 4, just here, and we have the function itself equaling to 4 as well. So we've got 2 times by negative 4 times by positive 4. That's going to equal to negative 16 times 2, negative 32. Okay, next question. We are asked for this integral of fx plus 2. So we're going to split up that integral. We're going to go 4 to fx dx plus 4 to 2 of 2 dx. So this is going to be, we don't know what f of x is, so we're going to use the integral function here, f of x from 4 to 2 plus 2x from 4 to 2. Now if we evaluate that, we've got f of x at, f of 4 minus f of 2 plus 2 times 4 minus 2 times 2. So we know that f of 4, we have got that one here. F of 2, we've got that one here. So we're going to end up with 12.8 minus 10.4 plus 8 minus 4. Okay, so we are going to end up with 2.4 plus 4, that's 6.4. Okay, so for this question, we have another fundamental theorem of calculus question. So by the fundamental theorem of calculus, we are taking an integral. So we are going from f of t to f of t. Then we're taking the derivative again. So we're going to get back to the original function. Integral, integral and derivative. So all we need to do is simply evaluate f of x when x equals to 4, x equals to 2. So this is simply just going to be f of 2, which we can read off the table of values is 4. Determine the x coordinates of any stationary points and whether or not they are local maxima, minima, or points of inflection. Justify your answer. Okay, so we know that what we're looking for is when the derivative equals to 0. So let's have a look for points where the derivative equals to 0. I'm going to get rid of these for now. We have got this one here, when x is equal to 1. We have got this one here, when x is equal to 4. So let's have a look at our table here. We know that the derivative is equal to 0. We don't know what the value of the function is, but we do know the second derivative. So one of our solutions is going to be at x equals to 1. So at x equals to 1, we know from this information about the second derivative here that the gradient is decreasing over time, right? The rate of change of the gradient is negative. That means that the gradient is decreasing. So if the gradient is getting from positive to smaller positive to negative, then that is going to imply that it is a local maxima. And so we're going to write local maxima, brackets, f double prime of x is less than 0, implies that the gradient is decreasing. Now our second one at x equals to 4, we have that the second derivative is equal to 0, so we must see that that is inflection point. F double prime of x is equal to 0. Okay, now we are looking for a possible graph of f of x for in the domain that we've been given. So we'll start just by plotting the points we know. We know that it is 4 at x equals to 2, so we'll put that in now. 4 at x equals to 2. Oops, wrong axis. Equals to 2, we've got 4. And we know that at x equals 4, we've got 0. We don't know any of the other values definitively. So let's have a look at what's happening to the function. So we know that, no, that was right. So we know that the function has a maxima at x equals to 1. So we know that, we don't know what exactly it is, but we know that it must be higher than this point here, because it must be a local maxima. So I'm just going to plot it over here. Now we know that the gradient is increasing before then, right? So the function is increasing before then because the first derivative is positive. So all we need to mark in there is some kind of upward slope. Now excuse that awful line. Let's try that again. All right, now for x equals to 2, we already have that marked in. For x equals to 3, we can see that the gradient is negative, but it's getting less steeply negative, but we don't really have any other information apart from that. So we're just going to assume that it is steadily decreasing, maybe a little bit more gently, down to here. Now we know that we have our inflection point at x equals to 4. Now after that, when we get to x equals to 5, we know that the gradient starts decreasing again and more steeply. So we're going to mark that in as the gradient decreasing all the way down, something like this. Oh, and since it's a fixed domain, we're just going to leave that as a dot rather than an arrow, like this. All right, that is all the questions for the 2023 Calculator Free section. I hope that was a helpful explanation. We are also going to work through the Calculator Assumed in the next week, so stay tuned for that. Happy studying.
Thank you for watching. My name is Henry, part of a team at Elucidate, a non-profit organisation that helps young people succeed at school. If you would like to see more chemistry videos, click up here. If you would like to learn more about us or support us, click down here.